All right, so we just did quiz number 3, your last quiz of the semester. Last things on your to-do list for the course is homework 13 is due on Friday, and then the final exam is next Tuesday. Any questions? I've been plugging along on grading the projects. I think I'm about a third of the way through them so far. I'll continue that this afternoon. I've given some pretty high grades so far. I think, the trend continues. People did a really nice job on the reports. The calculations look great. So I'm hopeful that I'll continue just handing out A's on the project because I really like to see your success in design on that. All right, we're going to talk about open channel flow through circular conduits. And the geometry of a circular pipe makes things tricky when the water isn't all the way full to the top of the pipe. You know, if the water is all the way full to the top of the pipe, then actually the geometry is very easy. You know, area is just pi d squared divided by 4. Hydraulic radius is just diameter divided by 4. I mean, the geometry, if it's full, is easy. But sanitary sewers, which carry wastewater from people's homes towards a treatment plant, or storm sewers, very rarely are going to be full. And so figuring out how big the pipe should be is a little bit more challenging as we combine Manning's equation, which describes flow through an open channel, and the circular conduits. So sanitary sewer systems are buried and they are fully enclosed, but they're vented to the atmosphere because of the manhole covers, because of the openings on either end. They're not under pressure. So we don't use Darcy-Weisbach equation for sewer pipes. We don't use the Hazen-Williams equation. We use Manning's equation to describe the flow through sewer pipes. And just some terminology that is important to understand. A service connection is the line between an individual customer and the distribution network. So what we're looking at here would be kind of the main sewer line, and these lateral pipes would come in from homes and businesses and tie into the main connection. And then manholes are spaced every couple hundred meters to provide access for cleaning out the sewer, for removing blockages. The thing about water flow through these sewer pipes is that they lay them out on a relatively shallow angle because they don't want the pipes to be getting deeper and deeper and deeper because, number one, it costs a lot of money to excavate a deep trench where they put the pipes in. But then the deeper the pipe gets, they're eventually going to have to lift the water up at the treatment plant or at intermediate pumping stations. And so by and large, unless you're in a city that's already steep, here in the floodplain part of Huntington, the sewer and storm sewer pipes are laid out relatively flat. And one of the impacts of that is that the water flows at a low velocity through the pipe and things settle to the bottom, especially when at the nighttime hours when there's a really low flow rate. Then sediment and debris that inevitably ends up in sewers sometimes can settle to the bottom of the pipe and just become stationary. And so hopefully what we'll see is that during a high flow period of the day, or maybe during a storm event, a big surge of water comes through the pipe at a higher velocity and scours any of that settled debris. But inevitably there's going to be a buildup, especially if you've got greasy wastes, like if there's oil or cooking grease that gets into the sewer discharge. It tends to stick to the bottom of the pipe. And so to prevent clogging, we have to have these manholes where people will go and inspect and clean the drains from time to time. The design of sewers starts with trying to estimate how much water you need to put into the pipe network. Like if you think about when you're developing a new part of town, like you did on your project, you were sizing the pipes that take water to people's houses, and to do that you were evaluating how many people there are going to be, What are their behavior patterns in terms of the way that they use water? So the same kind of analysis occurs when you're figuring out how big should the sewer pipes be that take the water away from people's homes. And what makes it complicated is that sewers, just like water pipes, are going to be in the ground for a very long time. It's inconvenient to replace them. And so a lot of sewers are sized with the future build out in mind. And so they're not looking at how much wastewater is being generated now, but what they'll evaluate is how much wastewater is going to be generated at the end of this pipe's design life, in 50 years or 100 years, perhaps if the zoning laws change, and what right now is low density housing, is there any possibility whatsoever that it can be reclassified as high density housing, and that there could be a high-rise residential tower where right now maybe it's just in a single family home. And so looking at all those factors, you would evaluate how much water is going to be generated. And one of the things that's similar with wastewater pipe sizing as there was with drinking water pipe sizing is that there are variations in the flow from the middle of the night where the flows are low to the peak hours. There's going to be certain periods where a lot of wastewater is entering the system all at once. And there are complicating factors that we wouldn't see in drinking water pipe sizing. In drinking water pipe sizing, the flow demand is strictly determined by human use patterns. We assume, for example, that if there's a crack in the pipe, they'll just go fix it, right? That wouldn't be tolerated. The water's too valuable, and there's a risk that if there's a water pipe that's leaking, besides the fact that it's going to reduce the pressure beyond the leak, and that's a problem, and beyond the fact that it's just wasteful, that water could cause damage. If there's a cracked pipe, it potentially could cause soil erosion, and the road could cave in, or there could be a landslide or something. So leaking water pipes that are delivering drinking water, they get fixed. But broken sewer pipes aren't always fixed in that same way, because we don't know if it's broken because there's no pressure signal. We can know if there's a crack in the pipe downstream of a drinking water pipe because suddenly people's pressure is worse than it was before. But when you have a cracked sewer pipe, the people don't notice it who are adding wastewater to the network, at least not as directly, not in the same way. So when you've got cracked pipes, then groundwater can leak into the sewage, into the sewer pipe. And that's what we call infiltration, when water is getting into the pipe that shouldn't be there. And it kind of adds some baseline on top of the flow that humans are going to be contributing to the sewer. Groundwater tables can rise and fall, and so it is possible that during dry weather, if the groundwater table falls, that you wouldn't see inflow, and then during wet weather, as the groundwater table rises, maybe the groundwater would submerge the pipe in a way that it isn't always submerged. So there can be some variation in infiltration. And then inflow are flows that are coming into sewer pipes that aren't necessarily like the main wastewater constituent that people are generating. So like if you have a pump in your basement to try and make sure that water doesn't get into your basement, like a foundation drain, and you're pumping it to the sewer, that would count as inflow. Or openings in the manhole, like the little vents that they have in manholes, sometimes rainwater can get in there, and that contributes to inflow. Inflow can also be where people have illegally connected to the sewer without paying for the service. Or sometimes it's just unknown connections, like old pipes that maybe go to a neighborhood that no longer has any homes, and they just never bothered to remove the pipe, and it over time cracked. And so inflow varies more with wet weather events than does infiltration, but we have to account for the wastewater that humans are intentionally putting into the system, but then also this collectively is called I and I. I&I, infiltration and inflow. So that has to be accounted for as well. So here's a picture on the right of somebody's got a connection between their roof and it's going to be going down to the sewer. And here in Huntington, about 10 to 15 years ago, there was a big push within the city limits to encourage people to disconnect their roof drain spouts from the sewers, because the sewers are over capacity and they were backing up a lot. They discharge into Four Pole Creek. 10 and 15 years ago, they had a problem with the sewer pipes backing up into people's basements. They more or less got that sorted out by installing like one-way flow valve, check valves into people's homes that were in those low-lying areas that were subject to backflow. But I think, you know, maybe they provided some incentives. They were offering people rain barrels if they disconnect their roof drains to going into the sewer. So that's just something you don't necessarily need to have going to the wastewater treatment plant, because, you know, there's nothing toxic or dangerous about the flow that's coming off of roofs. People don't want it discharging right next to their foundation, but as long as they kind of just have the spout discharging a few feet away from the foundation, then it shouldn't cause any risk to the structure itself. And then here's a picture taken from a camera, an inspection camera, that you could see just this water seeping in from cracks in the pipe. So that would be an illustration of infiltration. So the way that you evaluate how much water is going to come into your sewer is oftentimes just stipulated by city codes. Like, local ordinances can vary from place to place. And so this shows, for example, in Milwaukee, they tell you that when you're sizing a sewer pipe in Milwaukee, you should provide enough capacity in the pipe for 1,000 liters per person per day. And that's really high. I don't know if that's still the value in Milwaukee. You can see that this data was from 1982. But the main thing that it highlights is just the variation from place to place. So for example, in Berkeley, they're saying assume 350 liters of discharge from each person in the city of Berkeley. And then there are some additional allowances made for infiltration and inflow depending on where you go. It's kind of interesting here in Des Moines, they suggest that there should be some variation based on the size of the population. So there's 380 as a baseline, but then a correction factor for how big the area that's being drained is in terms of population. And the reason why population would maybe be a factor that you'd account for is that if you have a really big population upstream, then it's more likely that they're not going to all be using water at the same time. Like in small communities, people tend to have the same working schedules because there's not as big a variety of employers. But in like a city, just using New York City as an example, you've probably heard the saying that New York's the city that never sleeps. There's people who are always awake. And so a big city tends to have not only geographic reasons why the wastewater has fewer peaks, but also population-wise, it's going to be less peaking the bigger the city is. And so that also accounts for how much water is going to be used. So you have to know population density that's planned for the future, along with whatever the assumption is for the per capita discharge to the storm sewer or to the sanitary sewer from people. So you'd maybe evaluate how many people per acre or hectare they're going to be, and then use these factors to come up with the total amount of wastewater that has to be accommodated in the pipe. There's a wide variety of ways that wastewater is accounted for in commercial areas and industrial areas. Sometimes it's based on the size of the area that's being serviced. Sometimes they'll look at the individual industrial areas that are being planned, and there are some industrial facilities that will have their own wastewater treatment and discharge system. And this was common when I used to live over in the United Arab Emirates. A lot of hotels would have their own wastewater treatment plant right there just only for their hotel. And it ended up saving them money in the long run, just because they could operate their own in-house wastewater treatment plant cheaper than they could either have the waste hauled away or the fees that the municipalities were going to charge them. So infiltration and inflow, there's different ways that you can account for it. Sometimes you'd have it based on the length of the sewer. So here this is saying can be computed on the basis of cubic meters per day per kilometer of sewer line. Sometimes it's just based on the area that's being drained rather than based on the length of the sewer. And there's a lot of regional variation in how much infiltration and inflow. Like when the sewer pipe is being put in, if inspectors who are evaluating the contractor's work are really careful to make sure that the trench is bedded correctly, that it's on a good slope, and that there's a nice flat gravel bed underneath the pipe, then the pipe, which is generally made out of concrete, sewer pipes are, it's less likely to crack if the base of the trench is laid out with a lot of care. But the less frequent the inspection, the more hurried and rushed the contractor is, it's more likely that the bottom slope of the trench is going to have variations, and then over time, as the pipe settles onto that foundation, it's going to crack because there may be a low point in the middle, for instance, that causes that brittle pipe to crack. So here are some peaking factor models that have been proposed over the years that just take into account how population sizes would maybe impact the peak flow rate that you'd see and the minimum flow rate you're going to see. And this is similar to that idea that I introduced earlier, that the larger the population, the closer your peak flow is to the average flow. So you're likely to see a big discrepancy between the peak flow and the average flow in relatively small towns. But then the larger the population size, the closer together the peak and the average are, because of the geographic averaging. And by that what I mean is, if you've got water spread out over a really large area, there's a travel time from when you flush your toilet until the water, that flush arrives at the treatment plant. If you're in a small town, then the travel time from when you flush to when it gets to the treatment plant is pretty small. But if you're living in a very large, spread out urban area, like Houston, for example, from when you flush your toilet to when the water gets to the end of the line and it's at the treatment plant, it could be several hours. And so the bigger the population, that geographic effect is amplified as well. Okay, so as I mentioned, the hydraulics of circular sewer pipes are challenging because the water is not usually flowing to the top of the pipe. There are exceptions to that, though. I want to show you this video. Point that sometimes water flows through a sewer pipe at night and there's a very low flow rate, and other times it may be rainy weather and people are contributing a lot of water to the sewer in the evening when they're washing dishes, taking showers, doing laundry, and so on. So if we look at the cross-section of a circular pipe, we'll describe the circular pipe as having some diameter. But most of the time, the water's not going to be up to the very top of the pipe. Most of the time, it's only partly full. And so the way that we deal with that in terms of calculating the area is by measuring the angle of the water surface in terms of radians. And so, for example, if the water was up to the middle of the pipe, then you would have pi radians. So if it was halfway full, it would be pi radians. If it was all the way to the top, it would be 2 pi radians. But if you know the angle, here theta, then you can calculate the depth of the flow. So here it's described as h. Some references would call that y, the depth of the water in the pipe. But the point is that d is the diameter of the conduit that the water is flowing through, whereas the actual depth here is h. And it's a function of the angle. So once you know the angle, then you can determine the depth of flow, the cross-sectional area, the wetted perimeter. You can determine the top width. So how wide is that water? And when you get up to halfway full, the top width would be equal to the diameter of the pipe. But what's tricky is when we try and put this into Manning's equation. This is what Manning's equation looks like when we substitute in the unknown area, the unknown wetted perimeter as a function of the angle theta. So what our approach is going to be is usually we'd be given some flow rate and a channel slope, like what's the slope of the pipe. And we'll know what the pipe is made out of, so its material. And so we're going to find theta and then determine how deep the water is. And so we'll do that when we get together on Wednesday. We'll go through a couple of examples dealing with this partly full pipe hydraulics.